The singular value decomposition of a matrix is given by this form, U sigma V transpose. Now, U is an orthogonal matrix that holds a basis for Rm. These basis vectors are called left singular vectors, and obviously they're on the left of that matrix sigma. This matrix V holds an orthogonal and orthonormal basis for Rn, and that is the input space, if you want to think of it, whereas Rm was the output space, if you wanted to think of it that way. This holds the right singular vectors. And they're right singular vectors because that matrix V is on the right of this sigma matrix. Now, this sigma matrix is, we call it diagonal, but is not really diagonal. D is some R by R diagonal matrix that holds the singular values, the non-zero singular values of the matrix, and everything else is 0, just to make all the dimensions work out. So this is n by r, and this dimension here will be m by r. The singular values are important, and they're going to hold a lot of information. But before we get into any of this, let's actually find a singular value decomposition for a matrix. Now remember, any matrix has a singular value decomposition, and singular values are not eigenvalues. In some way, they will tell us some information, kind of related, but they are a next best thing. So here's a 3 by 2 matrix. We're going to form the product A transpose A. So this will give us, we'll swap the columns and rows out. So we'll have 1, 1, 0, 1, 1, 0, multiplying with the original matrix here. And remember, this is 2 by 3 and 3 by 2, so we're expecting to get a 2 by 2 matrix. So what we'll get is a 2, a 1, and then another 1, and then a 2. And as advertised, it is symmetric, as it's supposed to be. Now, a singular value decomposition is built off of this fact. And it's now going to tell us that, okay, this matrix G can be orthogonally diagonalized. So that means we can find an orthogonal diagonalization. We're going to need the lambdas, and we're going to need the eigenvectors for this matrix. So we'll go ahead and we'll solve for the lambdas. 2 minus lambda, 1, 1, 2 minus lambda has to be 0. So we'll get 2 minus lambda squared, subtract 1 is 0. This is going to tell me that the absolute value of 2 minus 1 is 1. And so that's going to be 2 minus lambda is plus or minus 1. So I'm going to get two simple values coming out of here. So I'll get lambda is 2 plus or minus 1. So that means lambda will be 1 and lambda will be 3. So those are the two eigenvalues of the symmetric matrix G. They are going to be related to the singular values. So the singular values are going to be like this. So the singular values, if lambda 1 is 3, then sigma 1 will be the square root of 3. If lambda 2 is equal to 1, then sigma 2 will be the square root of 1, which is just 1. So those are the singular values of the matrix. Now, we need the eigenvectors. So that means we'll solve G minus 2I into V is 0. And if you do this, you can go ahead, plug this in. You'll get negative 1, 1, 1, and 1, a negative 1. And this will be the case when lambda is equal to, sorry, there should be a 3 when lambda is 3. So you can row reduce this 1, negative 1, 0, 0, 0, 0. And that'll tell you that V1 should just be 1, 1. Now, we want to normalize this. So perhaps we should call this W. And then V1 is just going to be 1 over root 2 times this 1, 1. That's the first eigenvector. Now, when lambda is equal to 1, what we'll get is 1, 1, 1, 1, 0, 0. You could row reduce this as follows. And you'll get the vector W is going to be 1, negative 1. And if you normalize it, you'll get V2 is 1 over root 2, 1, negative 1. So this tells us the columns of the orthogonal matrix V. It's 2 by 2, and this has to do with the output space. My matrix A has 3 columns, 2 rows, and so I'm going to need 3 input vector with 3 entries, and an output vector will be produced with 2 entries. So what this is going to tell me is that V1 and V2 is an orthonormal basis for R2, the sort of the output space if we were to multiply A times X. This will also have to do with the column space of the matrix, but we'll get to that in a second. Now, we need all of these UIs, and that's going to be 1 over the singular value AVI. Here, each UI you're going to see is going to live in R3. So for example, U1 is going to be 1 over sigma 1 AV1. So that's going to be 1 over root 3, our matrix A, 1, 0, 1, 1, 1, 0. And now we multiply it by that first eigenvector. And so that's going to produce the following. 1 over root 2, and we'll get a 1 and a 1. You can do this computation yourself here, and you'll find you'll get a root 6 over 3, root 6 over 6, and root 6 over 6 again. Each one of these has 3 entries. So as advertised, it lives in R3. 1 over sigma 2, AV2. You're going to get 1 over 1, 1, 0, 1, 1, 1, 0, times this 1 half, 1, negative 1. Do the computation. What you'll end up with is 0, negative root 2 over 2, root 2 over 2. We're out of singular values. Now, we've got a bit of a problem. We need to find some U3 that is orthogonal to U1 and U2 so that we can construct this orthogonal matrix U. Essentially, what we're trying to do is now find an orthogonal basis for that input space, for those vectors U. Our options, we are guaranteed that we can use the Gram-Schmidt process to find U3 by way of projections. But it's a bit too much work here. We're just going to try to do this directly. You might say, well, how? How should we do this? Now note, if we take these vectors here, U1 has this factor of root 6 everywhere. So if I were to multiply everything in U1 by root 6, I'd get something that looks a lot easier. It's going to be 2, 1, 1. And if I were to take everything in U2 and multiply it by root 2, I'm going to get a vector that's much easier to work with. 0, negative 1, 1. These two vectors are still in the same direction as U1 and U2. It's going to be easier to find U3 with these. So we need some sort of U3. Let's say it's got these components here, x, y, and z. We need that root 6 U1 dotted with U3 is 0. And we also need that this root 2 U2 dotted with U3 is 0. So if you want to think about it, what we need to do is solve this system. We need to solve the following system. 2, 1, 1, 0, negative 1, 1. When I dot it with this vector here, it has to produce zeros. Effectively, that's what's happening. So what we need to solve is this system. And we can simply go ahead and row reduce this and try to come up with a pivot here. So if we add the second row to the top row, we'll get 2, we'll get a 0, we'll get a 2, 0, negative 1, 1. And if we scale this again, 2, 0, 2, we'll get a 1, 0, 1. 0, 1, 0, 0, 1, negative 1, 0. And we should find very easily that C1 is negative C3, and C2 is C3, and C3 is free. And so what you'll find in a very straightforward way is that this U3 is just going to be a 1, and a negative 1. And so you can normalize it, and we'll call this again U3. It'll be 1 over root 3, negative 1, 1, and 1. And that means that finally we've got this singular value decomposition. U is going to be U1, U2, and U3. And this is going to form an orthonormal basis for R3. And if you reassemble all of these bits, you'll find this is possible. The only thing we haven't done is formed this sigma matrix. It has to be 3 by 2. It's going to have a diagonal with the singular values down, and then it's going to be padded with zeros to fill in the rest of the dimensions. Once we've got that, that is the process by which we are going to build a singular value decomposition. Now, ultimately, you're probably saying, why do we care? Why on earth are we doing all of this stuff? The singular value decomposition is useful for a bunch of stuff. Finding out the rank of a matrix, image compression. Obviously, you've seen here finding orthogonal bases. Just briefly about the rank here, if you want to think about it, we talked about AV1 all the way down to AVR. These are these are orthogonal, which means they are linearly independent. And if my matrix A is m by n, that means my vector v, all of these vi's have to be in Rn. All of these vectors exist in Rm. So this set is linearly independent in Rm. Turns out we want to know if they span something. Now, they're linearly independent, but more importantly, each one of these things is an element in the column space of A. Remember, the column space is the set of all linear combinations of the columns of a matrix. And so each one of these things is a member of the column space. But do they span the column space of A? So any vector in the column space has to look like this. It has to be some linear combination of those vectors. The details are probably a wash for you at this point, but remember that some of these vectors were automatically set to be 0. And in fact, all of these vectors were the 0 vector after R, the non-singular one. And so that means that Y is in the span of these ones. And the point of the story is this set of vectors, which are just the U, are a basis for the column space of A. And because there are R of them, that means that the dimension of the column space of A, which is the rank, is equal to R. So as one simple example in real life, when people need to figure out the rank of a matrix, what they do is they find the number of non-zero singular values. That is the best way to determine the rank of a matrix. One small example, but singular value decomposition has a lot of uses, especially now in data analysis, data science. It's a very useful factorization.